So today we have with us Mikel Artetxe. Let me tell you a little bit about him. Mikel is a research scientist at FAIR, Meta AI, where his primary area of research is multilingual NLP. Mikel was one of the pioneers of unsupervised machine translation and has done extensive work on cross-lingual representation learning. More recently, he's also been working on natural language generation, few-shot learning, and large-scale language models. Prior to joining FAIR, Mikel actually did his PhD at this faculty and within the Isha group, that you guys here already know, and interned at DeepMind, FAIR, and Google. He's done a lot of more things, but I'm not going to list now because what we really want is to listen to what he has to say. So, Mikel, thank you very much for being with us today. And the, let's say, screen is yours.
Thanks for the introduction, Nora. Let me share my screen. Okay, I think you should be seeing my screen now. Okay, great. So yeah, in this talk, I'll be trying to answer whether a scale is all we need. And I guess like if you work on NLP, you will be familiar with this trend here, right? Like basically over the last few years, the size of our models have been growing almost exponentially. And the community seems to be somewhat like divided around this. So on the one hand, I think it's fair to say that there is like some hype with like people arguing that maybe our large neural networks are slightly conscious, or maybe not just slightly conscious, but fully sentient. And of course, like according to Elon Musk, we'll have AGI by 2029. But on the other hand, there are also like some people that are more skeptical and refer to language models as stochastic parrots. And also some people that would argue that, yeah, maybe BERT and all these models are great, but they won't get us to full natural language understanding. And of course, according to Gary Marcus, deep learning is just hitting a wall. And then, of course, I guess like there are also like a bunch of people, and perhaps like the majority of the people that are not like in either the sides and are more like in the middle of this, perhaps feeling like disoriented at times, like trying to figure out what to do and how to deal with the fast pace at which things are changing. So in this talk, I will just try to give like my perspective around this, and based on some of the recent work that I've been involved at, and try to share that with you. And the way I will structure the talk is by going through some of the points that the scaling skeptics would typically bring up and try to comment on those. And the first point that I wanted to discuss is this idea that scaling is not proper science. It's just like engineering, right? And I guess what this reflects probably like a change of paradigm in our field over the last few years. So we take AlexNet as an example. As you probably know, AlexNet was this paper from 2012 that basically revolutionized computer vision. It improved like the previous state of the art by a large margin, and it was sort of like an inflection point at which like everyone kind of reconsidered what they were doing and decided to move to doing deep learning. And it's interesting that this paper had just like 3 authors, all the 3 from academia, and the first author was a PhD student. In contrast, if you look at some of the most influential papers in the last few months, so Palm maybe could be a good example of that. And as you can see, the story here is totally different. So this paper has a long list of authors. I'm not sure like how many exactly, but I think it's at least like over 50. They all work for Google. And as you can see, it's like basically like a large like dedicated team working on scaling language models. And you can see that there's like a big investment, a big team effort, a big structure um, behind that. And it's something that nowadays can only be accomplished in few places and mostly on big industry labs. It's not something that, like PhD students can't do, just as like Alex was able to train AlexNet. So I guess this can be like frustrating, maybe, but I think if we broaden our perspective, we might be able to find like similar examples in other fields. So of course, like I'm not an expert in the field that I'm going to talk about, so maybe I might say something that is not like accurate. But if I'm not wrong, when Peter Higgs theorized what we now know as the Higgs boson in 1964, he used to be the only author of his papers. But in contrast, when the Higgs boson was actually discovered, it was observed for the first time in 2012, the resulting paper had so many authors that the full author list didn't fit in the first page of the paper. So they had to put the authors in an appendix. And yeah, here is that appendix. It has like 10 pages. And that's not even including the affiliation of these authors. It's crazy, as you can see. And it's not just that physicians like, put in a lot of names in their papers. If we look at like what was behind like this discovery, this discovery was made in the Large Hadron Collider at CERN, which is this like huge tunnel. I think it's 27 kilometers long. And I have no idea how it works, but I'm pretty sure there was like some very heavy engineering involved in building this thing and making it run. Yet, like when the Higgs boson was discovered, like no one despised this discovery, arguing that that was not proper science; it was just engineering. In fact, like 1 year after after this discovery, Peter Higgs received a Nobel Prize for his contributions to science. So coming back to our field, yeah, I guess that scaling requires heavy engineering, but sometimes science requires engineering, and that's something that we personally might be more or less interested, but it's necessary, it's important, and it's certainly not an easy thing to do. So I think we should not like look down on this engineering type of work. Now, someone might say that, okay, yeah, like I understand like a scaling maybe is important or it has to happen at least and someone has to do it, but I don't find it like very interesting myself, right? So I'm not very interested in, like doing all this like low level, like optimization stuff, scaling stuff, dealing with the infra and all that, just to get like the next model size, like a model like this is even larger than the previous one to hopefully get like a slightly better results in some random benchmark. I think that's like that research line is kind of empty. So some might argue that way at least. And I think that's a fair point. I kind of feel that way as well. But at the same time, I think that scaling can also come with its own interesting scientific questions. And I would like to like share some of like the work that I was involved at around scaling, where some of these questions arise. So yeah, the outcomes of this project were published in this paper here. And of course, the project at the beginning involved some engineering. we trained models with up to 1 trillion parameters in the project. And in order to enable that, we had to deal with things like pure FP16 training. The idea being that like typically models are trained with like mixed precision, but here we train them like everything FP16. But if we do this like naively, there are like numerical issues. So there are like basically some tricks that you need to do to make this like stable and like this way, like you're able to save like about half of your GPU memory without sacrificing on like model quality and convergence. Another thing that we had to do is implement what we call fully sharded data parallel, which is basically an implementation of the zero approach that Microsoft introduced. And the idea here is that these models are typically trained using data parallelism, where we have like multiple GPUs, right? And each GPU has like its own full copy of the model and processes like a different set of examples in each batch, and then the like gradients are synchronized or like are propagated at the end of each epoch. So of course, like if we want to train like very large models, then these very large models won't fit like in a single GPU. So this is no longer feasible. So what we can do instead is like split all these parameters, also the gradients and the optimizer states across the different GPUs, and then like basically pull them from the relevant GPU as needed. So of course, like if we do this naively, we would be like communicating across GPUs the whole time, and that would be very inefficient. But there is like a smart way to do that, and that's basically what Zero proposed and what we had to implement here. So yeah, there's all these like engineering type of stuff that one has to do. We also explored something at the architecture level with mixture of experts. So in case you are not familiar with mixture of experts, these are basically sparse models where like we only activate a subset of the parameters for each token. And this allows to grow the number of parameters without growing the number of flops. So to be more precise, as you probably know, transformers, like each transformer layer has a self-attention sublayer and a feed-forward sublayer. So here the self-attention sublayer remains the same. And what we do is for the feed-forward sublayer, instead of having like a single feed-forward network in each sublayer, we have many of them, multiple feed-forwards, and we call each of them an expert. This is where the name mixture of expert is coming from. And what we do is for each token, we decide which of these feed-forward networks we are going to use. So there is like some very simple routing mechanism that is used to decide where to send each token. So this means that the total number of parameters now can increase by a lot without increasing the amount of compute that we need to perform to process each data point. And that's because at each like transformer layer, we are only activating like either one or two of the expert or one or two of the feed-forwards as opposed to all of them as like standard dense models would do. So using all these techniques, we trained a bunch of models. We took like GPT-3 as a reference. We tried to replicate most of their models. Like these were dense models, so not using like any of the like latest like MOE stuff that we just discussed. And then like we also trained like some MOE models that are flop matched with dense ones. So everything is the same between like dense models and MOE models are the same row in the table. except that the MOEs have like, in this case, 512 experts. That is like 512 people words in each layer. And then we evaluate these different models in different settings. So to start with, we evaluate them on in-domain validation perplexity. So we just take like a held out set of our corpus and evaluate how the models perform as a function of a scale. And we compare like MOVs and dense models. And as you can see, I mean, first, like we find that large models do better. I guess that's not a surprise. But we also find that for the same compute budget, for a given compute budget, MOE models perform substantially better than dense models, which is interesting. I think it's worth keeping in mind that, you know, even if we associate like a scale with like high compute cost and all that, like there's also like research to be done to try to scale more efficiently. And I guess sparse models like MOEs can be one direction. It's not the only one, of course. Like we could also like some other direction could for instance be like retrieval augmented or like semi-parametric models, and I guess like there could be like other approaches that people might come up with as well. But in any case, like the picture, the final picture that we got was not as clear as what this figure here might suggest. Because when we ran the same experiment on some out-of-domain data, the trend was actually different. So here, like similar to before, like we find that the scale still helps, of course, not surprisingly, but we see that the difference between like dense and MOE models is smaller in this case. And not only that, but it also diminishes at the scale. So for small models, like dense variants still have like a considerable advantage. But as we scale up, the difference becomes very small. And it looks like if we further continue the scaling these models, at some point, like MOEs wouldn't be like any better than dense models. And this is interesting because this kind of suggests that MOE models and dense models generalize differently out of domain. In addition to that, we also evaluated the models in prompting. So there are like two typical scenarios which like language models are evaluated through prompting. So in zero-shot learning, we just like formulate downstream tasks as language modeling, and just like in this case, like fit this prompt to the language model and generate like the right completion. If it's like a multiple choice task, we just like score all candidates and pick the most likely one. And feature learning, we do like exactly the same, but I'm preparing a bunch of like labeled examples, which has been found to improve results. So these are the results that we get aggregated over like all the tasks that we evaluate in. So as you can see, we first like find that our dense models like are able to very closely match GPT-3. So that's good. Like we are kind of able to replicate GPT-3. And then like we also find that MOE models do better than like the dense counterparts for a given compute budget, which is also great. But again, we find like the same trend as before, that the relative advantage of MOE models tends to diminish at scale. And we can visualize all of this like more clearly here, where we are basically showing the speed up factor of MOEs in comparison with dense models. So the idea here is like, for instance, like a speed up factor of 10 at a given point would mean that MOE models can achieve the same performance of the corresponding dense models using 10 times less compute, or 10 times less training time. And what we find is that for in-domain language modeling, the speed up factor is large, right? It's I mean, it fluctuates, but it's around like 10 or so, which is great. For both out-of-domain language modeling and zero-shot prompting, it's much smaller, and it also tends to seems to diminish at scale. So at the beginning it's higher, and then it tends to become larger, like even approaching 1 as we scale up. And if we dig deeper and we look at like a specific like tasks and the specific like subsets of the corpus, of the validation corpus at which we compute perplexity, we find like a considerable variance. So these are for the this figure shows different subsets of the test corpus, the pile in this case. And we see that for some of these like sub corpora, the speed up factor is very modest. Like for DeepMind mathematics, for instance, it starts like around 2, but then at the end it's even below 1. So at the very end, dense models are even like very slightly better than MOE models in this particular data set. Whereas for some others, like common crawl in particular, the speed up factor is higher, and for the other two, archive and open subtitles, it's somewhat in the middle. In the paper, we have like even more subsets, but these are just like some illustrative examples. And what this suggests is that the closer the domain of your corpus is to the training domain, then the larger the benefit of the MOE models is. Whereas if you, if the domain is like radically different, then the speed up factor might be like smaller, like maybe even like close to 1, which means like no speed up. And something similar happens with prompting and different tasks. But I guess like it's even like more puzzling here. So like this case, for instance, we find that the speed up factor for Vino Grande is quite small. So it's like below 2. Whereas the speed up factor for Pika is quite high. It starts like above 7, and even like for the largest model size, it's around 4. And the interesting thing here is that it's hard to find like any principle like explanation for this behavior. Like what is it that is special about one like a data set or the other? Like we try to look at the domain or like maybe the task format or things like that, but we couldn't see like any clear pattern. So I think as future work, like it would be very interesting to try to better understand what is it that makes MOE models better in some like tasks or for some instances, but not for others. And another interesting observation that we made while we were experimenting with this was connected to the few-shot scenario. So this was published like in this other paper. And so as I mentioned before, the idea of feature learning is that we can prepend like some correct examples as context to the prompt. And this has been referred to as in-context learning, the idea being that even if we don't perform any parameter updates, any gradient updates, the model can leverage the information in the context to learn what to do, so to say. And what we tried then was just like randomly changing the output of these in-context examples. And so, like this will mostly be wrong now. And so intuitively, we would expect this to break the model, right? Like if we give it like some wrong examples, then the model will learn to do the wrong thing, or it will not be able to learn anything. So this will this should intuitively deteriorate performance. But that's actually not what we found to happen. So here we tried this for 3 different models, both for a few classification tasks and multiple choice tasks. So the blue bars correspond to the zero-shot scenario where there are like no in-context examples. And the yellow bars correspond to the standard few-shot scenario where we have like a few examples with the correct labels. And as we can see, and as expected, this works better than the zero-shot approach, right? So the few-shot examples help, and that's why the yellow bar is higher than the blue bar in all cases. Now, the surprising bit is the red bar, right? So for the red bar, we also fit some examples in the context, but the label is completely random. We choose it at random. And we find that that's still better than zero-shot learning. So even if the label is wrong, the model is able to somehow exploit those examples. And in fact, these red bars are only like very slightly worse or at par with the yellow ones, with using like the gold labels, which suggests that most of the benefit, if not all of the benefit of in-context learning does not come from the model understanding or exploiting the relationship between the input and the label, but from somewhere else. So if you're curious, we have like a few more experiments in the paper where we try to shed a bit more light into this. So I get so getting back to the original point. Yeah, I think that even if you are not the type of person that are interested in the lower level technical scaling part of things, I think that there are like some interesting research questions that arise when working with large language models. And we need not only engineers doing the core infra stuff, but also proper science and people doing research around all these questions. So moving forward, I guess another point that people tend to make is that this whole stuff is entirely impractical, right? Because training these large models, it's super expensive. Most people cannot afford doing it because they don't have the compute. It's also not good for the environment. And above all, it's just it will never be used because we can't deploy these models into production, right? It would be way too expensive. And I guess all of that is true, and ultimately we are constrained by all of us by the compute that we have and the environment that we are at, and it's unavoidable to account for that when deciding what to do. But I think it's worth keeping in mind that our notion of large and small is primarily based on what current hardware can do. And that's something that keeps changing over time, right? This is a paper from 1986, I think. It's considered the first paper showing that backpropagation can learn interesting representations, so to say. And the model that they trained in this paper had only 500 parameters, which sounds ridiculous from today's perspective. And that's because today we usually train models with a few million or a few 100 million parameters. So BERT large, for instance, had 340 million parameters. And it's interesting that this was considered crazy big when BERT came out. But nowadays we consider this more a standard or even small scale, right? And that's because we have these other huge models with 500 billion parameters. And that's what we now consider to be truly large. But I think, it's very likely that in some years, like this will be like the new normal, and we'll have like models with like many more parameters, and we'll be saying like, like this is like impractical, this is too big and all that. I think it's important to keep that in mind. And in particular, like I sometimes find it like somewhat ironical that it's mostly in industry that all this research around like large language models is happening, and that's understandable because that's like where the compute mostly is, I guess. But at the same time, like I guess by definition, we would expect industry to be more concerned about the practicality of what they do, right? And if all these big companies decide to invest heavily in scaling, it's because they expect that it will somehow pay off sometime in the future. And so I find it like a bit ironical when I sometimes hear people in academia kind of saying that all this work is kind of impractical because, of course, like it's totally understandable. Like people might be constrained, like they might not be able to do this research themselves, but they should also not be, I think, thinking or like overly concerned about the practicality side of things, and maybe like academia should try to keep like a longer term like a perspective or horizon in mind, and we do that. I think that what's large, what's small, what's practical, what's impractical would certainly change and change at a fast pace. And connected to that, I think that to kind of abstract away from like what the current hardware can do, and try to reason about like how large or small like our models are. We can maybe try to compare them with like our brain, for instance. And of course, like this is hard comparison, right? Because we don't have like real value parameters in our brains. But we do have synapses, which are connections between neurons. And apparently we have about like 150 trillion of those, which is much more than the 500 billion parameters that the largest language model has. So I guess this doesn't necessarily mean much, but I guess like at least on the surface, like it doesn't look like we are at a scale range that looks like completely crazy compared to how like truly intelligent like humans or creators are. Another point that I think is worth keeping in mind related to the practicality of scaling is that even if we tend to associate like maybe a scaling with like a slowness or like inefficiency, large models are more data and compute efficient. So this is like these are some results from the scaling laws paper from OpenAI, where they show that for a given number of tokens processed, large models consistently achieve better performance. And not only that, but if we are interested in achieving like certain performance, after a certain point, like it pays off to scale. So in other words, like the as we grow our compute budget, the most efficient model will always be a larger one. And so if we are interested like in compute efficient training, then and we assume that our budget will improve over time, then investing on scaling, investing on understanding how to scale efficiently, how to like take advantage of our hardware is something that we should be doing. I think maybe like there is one point that is like totally fair, which is that large language models are not accessible to everyone. Like very few people can actually train this type of models. In fact, like no individual can train this type of models, you really need like a large dedicated team. And I guess like it's a bit unfortunate, or at least like from my point of view, that our field has become like a lot closer over the last few years, and like actually most of these large models are not like public, right? There are like some paid APIs. In some cases, there's not even that. But for most models, you just can't like access them directly. And not only that, but like it's often also like difficult to know what's behind that. So on the paper, like the corresponding papers wouldn't give like much details about what data was used to train the models and so on. So that's true. That's unfortunate. But I think there is some hope, and things might be getting better, slightly better, very recently. So at least from our side, FAIR has been quite committed to open science. So all the work around like MOE scaling that I discussed earlier. So all those models are public. You can download them if you are interested in further exploring like these mysteries around like MOE generalization. You can download the models and try them yourself. And like more recently, we also I trained like dense models up to the size of GPT-3, and we also released all of our models. And of course, it's not just that, just us at Meta AI, but there are also like other initiatives like Big Science, other companies like Evolutionary AI that are doing like a great work in that regard. And I hope that as a consequence of this, like maybe others will also join this and start like releasing their models. And one last point that I wanted to briefly mention is this argument that language models like don't truly understand, right? And I guess the point here tends to be that yeah, maybe like these large language models can generate like nice looking text, and they can get like good numbers in all these benchmarks and all that, but they are not like truly understanding. They're basically exploiting some superficial like patterns in our data, but without the true understanding, they are fundamentally limited. And I think like all these debates like around like what's true understanding or not, or like even like whether the models are conscious or what that means and all that, like I think that's very interesting. That can be inspiring. It can be intellectually stimulating, but to me it seems to belong to philosophy more than anything else, in the sense that, you know, ours is an empirical field, and if you believe like these models have some fundamental limitations, you should try to build a benchmark and like prove that you know, empirically that such limitations indeed exist. I think that would be you know, better than like telling stories about like octopus like intercepting messages in the middle of the ocean and things like that, which is an interesting read, but like maybe like it doesn't allow to like directly build on top. And maybe another point that I think is worth keeping in mind is that, as far as I know, like, you know, like large models, of course, like might have like lots of limitations, but as far as I know, there's nothing that small models can do and large models cannot do. In other words, like all limitations that the large models have also apply to small models. But the reverse is not true, right? Like there are things that large models can do and small models cannot do. So in that sense, like large models seem to be like extremely better. And like yeah, connected to that, like there are all these like recent works like showing like emergent capabilities in large language models. which I find to be like super fascinating, where like basically smaller, like relatively small models, like models like up to some size, like obtain like random like performance, but then there is like a phase transition, and after that point, like a scale, like things kick off on a scale starts to making like a big difference. And so to finish the presentation, I also wanted to briefly discuss what my journey has been, how that has shaped my perspective around scale. I'm afraid I won't have time to go through this in details, but maybe I can try to very quickly tell the high-level story. I guess the starting point of this was this work from Mikel Artetxe, showing that you can train word embeddings in different languages separately, and then take a bilingual dictionary and use this bilingual dictionary to learn an alignment between the two languages. And then you can use the resulting proceeding word embeddings to induce translations of new words. So for instance, here you can induce that house is the translation of Etxe because it happens to be its nearest neighbor. That's great. Like there's some simple math that you can do to solve the problem. But at the beginning of my PhD, we asked ourselves like, okay, do we really need a dictionary? And we thought that the answer might very well be no, because we might be able to align the two spaces based only on their geometry. And that's because, if we just like naively put the green points on top of the red points, this looks like a bad solution. But if we rotate them, we'll eventually reach this other configuration that looks much better, right? Like it looks like this is like a good alignment between the two spaces. We don't really need any supervision to make this assessment. So for simplistic like artificial instances like this does seem possible. In the wild, like it happens to be like a lot more challenging, but we eventually managed to make it work. We also like, of course, concurrently with some other work by others. The approach that we developed was based on this like somewhat fancy notion of interlingual similarity distribution. So we basically computed the similarity between each word in each language and the rest of the words in that same language over the original embeddings, and then matched word pairs having a similar distribution to induce an initial dictionary, and then use this dictionary to learn an alignment using the traditional like Mikolov-like technique, and then use the aligned embedding to induce a new dictionary, and then iterate over that in a self-learning process. And this achieved like some decent results in word level translation. And then we also worked on like generalizing from word level into text level or like sentence level translation by using these word embeddings to initialize an encoder decoder network that we trained not in a supervised way, but used in an unsupervised way, using a combination of denoising and interactive back translation. So long story short, this was like a somewhat long journey where we had to develop like a bunch of like fancy techniques to get into a working system that worked like somewhat decently. Adding like some further steps, like even more complication, we were able to further improve on these results. But then something interesting happened, which is like this thing called like multilingual BERT came out. You probably heard of it. And like using a very simple approach, at least like conceptually, they were able to get like a good initialization that also worked for unsupervised machine translation when combined with iterative back translation. So in other words, like with multilingual BERT, you can just concatenate a monolingual data in different languages, train a mass language model, use that to initialize an encoder decoder network, and then train the model through iterative back translation, and that works as well as the like fancier method, like aligning word embeddings and all that that we developed. But there is more, because after that GPT-3 came out, and GPT-3 like only trained regular like left to right autoregressive language model, They didn't do like any of the fancy back translation or anything else than training like a vanilla language model, and that actually worked like better than previous unsupervised machine translation systems. And like more recently, when this Palm paper came out, they basically like further scaled the model, and they also like used some better quality and more quantity multilingual data, and that further improved results. And the results that we get now, like they are truly impressive, like more or less matching those of like traditional supervised machine translation systems. So it should be said that this comparison should be taken with a grain of salt. So these numbers are truly not like directly comparable because of differences in the evaluation metric. Also, like things are not comparable in terms of the training data used and all that. But still, I think we can make the point that scaling vanilla language models outperforms the best unsupervised machine translation system that we built over the course of my PhD. So I guess that's an interesting lesson, right? We could have gotten like there or like even better than there by simply scaling a very, very simple idea instead of like, you know, trying to like come up with like this fancier ideas that are very cool on paper, but like maybe not necessary when you can just like scale a very simple idea. So going back to the original question that motivated this talk, is a scale then all we need? So I don't have the answer of that, of course. I want to think that scale is not all we need, but it's something that we certainly shouldn't be ignoring, right? It would be stupid if we ignore like all these results from Palm and like GPT-3 that I just showed, and you know, kept doing like our like embedding alignment stuff just because it's cool and you know it's cheap and easy to do. Maybe like there might be like you know, good reasons to keep doing that, and you know, like these approaches like might be complementary, and there's like in fact like some work from OpenAI showing some of that. But you know, like we should be mindful about a scale as a factor, and that's it from my side. Now time for questions. Thank you.
Thank you, Mikel, for a very interesting talk. So we do have a couple of minutes for questions. So what about we start from a question from the room? Anyone? Yes, okay.
Can you hear me? So one of the big criticisms on these large language models is always that it's like a big black box. It's hard to know what is going on inside. So I was curious about your opinions on how this research can inform like how humans produce language. Like, because I come from a more cognitive perspective, and I'm curious how these models can be used on that side of the field.
Yeah, I would say like probably the same happens like about like our brain, right? Like I'm not an expert in neuroscience, but like I certainly have the impression that we don't know very well how the brain works, and maybe we don't need to know very well like how the brain works. So I'm not sure if this like is like a satisfying answer to your question. I think that there is like a some very interesting like analysis work, like you know, around like smaller but also like larger models, and that's all very interesting. But at the same time, like I think we should be mindful of like not trying to like anthropomorphize, or I don't know what's the exact word, like how these like models behave, and like you know, try to come up with like a very simplistic explanations of that, or like you know, like we start with some hypothesis and we basically like either like consciously or unconsciously like end up like torturing like the data so that like we have the impression that like this is truly like how the model is working, but that might be like not necessarily accurate. Yeah.
If anyone online wants to ask a question, you can write it on the chat, okay? So while you do that, if anyone wants to do it, maybe we'll have another question from the floor. Yes? Okay.
So, can you hear me?
Yeah, I can hear you.
Okay. Since you also work in multilinguality, I was wondering what about this discussion changes when we're talking about languages with different kinds, like different levels of resources, if anything changes, or yeah.
Yes, I think that's I think there's some echo. Okay, now it's good. I think that's like a very good question, and it's also like one of my primary interests at this moment. So like for all this like a scaling work like that is focused in English, like we are mostly compute constrained, not data constrained, right? Like compute is the main bottleneck at this moment, not data. We have enough data. We have the whole internet basically. But when you move to low resource languages, that's no longer true. We are mostly constrained by the lack of data, not the lack of compute. So if you try to train the best possible language, monolingual, at least a monolingual language model for a low resource language, after some point, like further scaling won't help, like different from English, just because you don't have enough data, and you will start like overfitting as you scale up. So I guess there's hope that like cross-lingual transfer can cover that to an extent, but I think there's still not like a principled understanding of that, and that's I guess like one of the like interesting scientific questions that it's out there, and hopefully like we'll be able to answer in the future.
We have, let's move to the questions we have in the chat. I think, Mika, maybe you can read them yourselves as well, but let me just read the first one, okay? So this is the question. What could be the contribution of linguists to these LLM? Is there work for linguists in this new age of LLM? Probably they could help to reduce the size of the models and need for a large amount of data. But if yes, how to do that?
I don't think we would necessarily like need to reduce the for data and compute for linguists to like do research with these models. Like of course, like you know, like it's probably not a good idea to put a linguist like doing the engineering work required to train these models. But I think there's like an awesome opportunity for linguists to take one of these language models that are supposed to be like you know so good, maybe like slightly conscious or sentient and all of that, and try to truly understand like what they do. Like I don't have like the best background to try to answer like you know all of the questions, like some of the skills and knowledge that a linguist has like might be like you know more relevant to try to get like a better understanding of how these models generalize and how these models behave. And I think like ideally this is also something that like you know it should not be like computer scientists like asking linguists like, hey, like you know it would be interesting if you could analyze this or that. Like hopefully like linguists will also find like you know like fascinating that like we have like this maybe like a bit intimidating, but at the same time like fascinating that we have like this like models that can do all this stuff, and they would be curious to try to try different things with them and see if they can also do like this other thing, or like I don't know, come up with some hypothesis and try to test it or whatever.
Okay, so we can see we have loads of questions on the chat, but I'm actually going to give an opportunity to someone here if you want to ask anything. Okay, just last question, and I'm pretty sure, Mikel, you can talk to the people online and answer all these actually pretty interesting questions.
Hello, can you hear me?
Yeah, I can hear you.
Yeah, so as far as I understand, this is language modeling. So you are modeling language, how to predict the next sentence. So how can you say, or people at other big industries say that this is slightly conscious? Like, that's my question. Like, so what, how is
Yeah,
consciousness defined in like Facebook or Google or Amazon, like stuff? That's my question. Thank you.
So yeah, I mean, I try to give my opinion like on this like throughout the talk. Like I my opinion is basically I don't have like an opinion. I think like that discussion, like are these model conscious or not, like that sounds like philosophy to me. And I try to do like empirical research. So unless like, you know, you can define like a consciousness in such a way that, you know, like can be like empirically like proven or refuted that our models are conscious, then I don't think that these discussions will. I mean, they can be like interesting, but like interesting in a different way. I don't think that like they will like lead us to like any direct like progress. And I personally I don't tend to think about like this type of things, and I also don't see people around me like working these models, like discussing like this type of stuff.
Okay, so I'm going to stop with questions here because it's already 11 o'clock. I don't know, Mikel, if you'd like to say anything just before we say thank you again and bye-bye.
No, I mean, just like yeah, thank you to all of you for attending and yeah, for inviting me. And like, feel free to drop me an email in case you have like any other questions.
Okay, so thank you very much, Mikel. It was a pleasure having you here today. Hopefully we'll meet again soon. And bye-bye, everybody.